Today we're going to be talking about using two new identities, or actually several new identities, that compose the sum and difference formulas. Our goal is to apply these to evaluate some exact values of trig expressions for different angles. There are some angles, the angles that have to do with special right triangles, that we're very familiar with the trigonometric functions of. For instance, sine of 30 degrees is equal to 1/2. There are other angles that we've only been able to approximate using a calculator. For instance, the sine of 75 degrees. Today we're going to talk about a way to use angles that we know to figure angles out that we don't know. Let's think about sine 75 for a minute. We don't have an easy way to get an exact value. We can get the approximation using a calculator pretty easily, but there's no way to determine exactly what that's equal to. We also know that 75 degrees is made up of two angles that we do know. 45 degrees plus 30 degrees equals 75. We know both 45 and 30. It would be wonderful to use the knowledge that we know. Sine of 45 degrees equals the square root of 2/2, and sine of 30 degrees equals 1/2 to help us figure out what the sine of 75 degrees is. The good news is that we can. The sum and difference formulas give us a chance to use two angles that we know the trig values of to figure out an angle that we don't. We have sum and difference formulas for sine, cosine, and tangent, and all 6 of them are listed on this slide. If you're interested in seeing where these come from, I'm going to do a derivation of how to get the cosine difference formula in video 5.3 alpha. It's not required for my course that you watch it, but if you're interested in a combination of geometric and algebraic proof, that's what you could look at. Okay, for the next few slides we're going to be playing with these guys to see what we can do with them. And let's start off by applying it to our initial question. How do I find the sine of 75 degrees? Let's set this up as the sine of 30 degrees plus 45 degrees. That's going to require our sum sine formula. What I've done here is just copied down the sum of two angles sine formula, which is those two angles, u and v, and sine of the sum of those angles equals sine of u times cosine of v plus cosine of u times sine v. When I plug my 30 and 45 in, sine of 30 plus 45, remember this is 75 degrees, equals sine of 30 degrees plus, sine of 30 times cosine of 45 plus cosine of 30 times sine of 45. If I substitute in values that I know, sine of 30 is 1/2, cosine of 45 is square root of 2/2, cosine of 30 is square root of 3/2, sine of 45 is square root of 2/2, and I simplify, I get the square root of 2 plus the square root of 3 times the square root of 2, all divided by 4. And we can verify this. If on a calculator I type in the square root of 2 plus the square root of 3 times the square root of 2, and then I divide by 4, I get an approximation of 0.966. If I check this by calculating the sine of 75 degrees, I should get the same answer, and I do. Let's try another example. If I were interested in finding the cosine of the angle, that is pi over 3 radians plus pi over 4 radians, I'm going to need to use the sum of two angles cosine formula, which I've listed off to the right. That's going to be cosine of the sum of two angles u and v is equal to cosine of u times cosine of v minus sine of u times sine of v. Most of you won't ever have to actually remember these. If you need to use them, you can look them up. So I'm going to list them every time that we do them out. Very few of you, those of you who are involved in any math competitions, might find it useful to find a way to keep these in your mind. Okay? So cosine of pi over 3 plus pi over 4. If I set that up, and plug in values, I get cosine of pi over 3 times cosine of pi over 4 minus sine of pi over 3 times sine of pi over 4. If I plug in these values, cosine of pi over 3 is 1/2. Cosine of pi over 4, square root of 2 over 2, minus sine of pi over 3 is going to be square root of 3 over 2, and sine of pi over 4, square root of 2 over 2. I end up with square root of 2 over 4 minus the square root of 3 times the square root of 2, also over 4. I can simplify this a little bit more and write it in a couple different ways. One of which I can factor out as square root of 2. Have this as 1 minus square root of 3 all over 4. Or I could write this as the square root of 2 minus multiply those two radicals to get the square root of 6 all over 4. Either one of these two is acceptable. To see if my approximation worked, I'm going to do square root of 2 minus square root of 6 on my calculator. Divide that by 4, and I get negative 0.259. If I switch my mode to radians, I can confirm my answer by taking the cosine of pi divided by 3 plus pi divided by 4, and I get negative 0.259, which confirms our solution. Let's look at another example. The tangent of 210 minus 45. This time we're going to use our difference of two angles tangent formula. That's tan of the angle u minus v is equal to tan of angle u minus tan of angle v divided by the quantity of 1 plus tan of angle u times the tan of angle v. So if I begin to plug this in, I'm looking at the tan of 210 minus tan of 45 over 1 plus tan of 210 times tan 45. Okay? When I begin to plug values in, tan of 210, if I want to think about this as a unit circle, 210 is 30 degrees below my negative y-axis and is going to have the points negative square root of 3 over 2, comma 1/2. Tangent is going to be y over x, which is 1/2 divided by negative square root of 3 over 2, which is going to come out at negative square root of 3 over 3, or negative 1 over the square root of 3. Okay? So I have negative square root of 3 over 3 minus the tangent of 45. That's where the x and y are equal. So that's 1 divided by 1 plus negative square root of 3 over 3 times 1. When I go to simplify this, I'm going to have negative square root of 3 minus 3 over 3 all over 3 minus the square root of 3 over 3. If I multiply this out, negative square root of 3 minus 3 over 3 times 3 over 3 minus the square root of 3. My 3's on the first denominator, second numerator are going to cancel out and leave us with negative square root of 3 minus 3 over 3 minus the square root of 3. To look at our last example for today, let's take a look at sine of 285 degrees. Now I know some angles that surround 285 degrees, but I don't know anything about 285. So the first thing I'm going to do is write this as the sum or difference of two known angles. And there are lots of different ways I can do this, as 225 plus 60, as 240 plus 45, as 330 minus 45. It doesn't really matter which one you choose. I'm going to choose 225 plus 60. So I'm looking at the sine of 225 degrees plus 60 degrees. I'm going to use my sum of two angles sine formula, which is sine of u plus v equals sine of u times cosine of v plus cosine of u times sine v. And if I begin to plug this in, that's equal to sine of 225 times cosine of 60 plus cosine of 225 sine of 60. Sine of 225 is going to be negative square root of 2 over 2. Cosine of 60 is a half. Cosine of 225 is going to be negative square root of 2 over 2. Sine of 60 is going to be square root of 3 over 2. I've got negative square root of 2 over 4 minus the square root of 6 over 4. Negative square root of 2 minus the square root of 6 all over 4 is going to be our solution. In most applications, you're not going to need to do this. We know we can use the calculator to come up with an approximation for any angle that is going to be suitable for most purposes. Where this is going to be useful is for algebraic purposes where you don't know one of the angles, or if you're trying to solve a trigonometric equation that involves the sum or difference of angles that are harder for you to deal with.